Confidence intervals for the mean and the t-distribution. When the population standard deviation is unknown, the sample size is less than 30, and the random variable x is approximately normally distributed, it follows a t-distribution. So this is the formula to find your critical value t. And we'll be using the calculators or our distribution table to find our critical value. The critical values of t are denoted by t sub c. And remember that lowercase c represents the confidence value, the confidence level, the percentage. So when choosing between the t or the z normal distribution, here are the conditions and what you would choose. So the conditions, if our sigma or our standard deviation, the population standard deviation, is not known, and we have a normally distributed population, or our population standard deviation is not known, and we have a sample size greater than 30. So what that means is we could have a sample standard deviation and our sample size be less than 30, and we would use the t-distribution, or we have the sample standard deviation and it's greater than 30. So it might not be normally distributed, but our sample size is greater than 30. Otherwise, we would be using the z-distribution. So in a z-distribution, we know the population standard deviation, and it's normally distributed, and our sample size is greater than 30. So when you're going to use the t-distribution or the z-distribution is based on these conditions. But in reality, our population standard deviation is rarely known. The degree of freedom. If you have a sample size is n, then t is said to have n minus 1 degree of freedom. And it's denoted as df to denote the degree of freedoms. This allows for discrepancies in our values for the standard deviation. So we use the degree of freedom to give us a true value. So a key note here is the bigger the sample size, that is, the bigger the sample size used to estimate our standard or population standard deviation, then the closer our t-distribution becomes to z. So again, remember the t-distribution, we have a sample standard deviation versus the population standard deviation. So if our sample size is greater than 100, our t-distribution will approach our z-distribution. So to find the critical value for your t sub c for a 95% confident level when the sample size is 15. So how you would do this is you first need to find your degree of freedom. So to find the degree of freedom, you take the sample size and subtract 1. So in this case, our degree of freedom would be 14. Then you're going to turn to the table and you're going to start with the degree of freedom column. And you're going to go to that value of the degree of freedom. And in this case, it's 14. And then you're going to use the level of confidence row, and you're going to go to where that confidence level is. And in this case, it's 95%, so it's 0.95. And where they intersect would be our critical value, our t sub c, which is 2.145. So if you were to use the table, that's how the table would work. So you never get a negative t-distribution value. But if you're using the calculator to find the critical value t sub c, and same example, we're going to have a 95% confident level with a sample size of 15. We're going to use the calculator, and to use the calculator, you're going to press the second VARS button and distribution, and you're going to choose the number 4 option. Now, in the TI-83 calculators, that option does not exist. Therefore, if you have an older calculator, you will need to use the t-distribution table to find your critical value. Otherwise, if you have one of the newer calculators, an 84 or above, you can use the calculator to find your critical value. So remember, the area represents the confident level, but you have to incorporate that piece of tail that is missing. So to do that, you take your level of confidence and you add 1/2 minus the level of 1/2 times 1 minus your level of confidence. That's going to give you that value of the tail. Remember, the tails, the two tails that are not filled in, is 1 minus C, our confident level, because our confident level is the area shaded under the curve. And because the tails are not in that confident level, to find our critical value, we need to incorporate that one tail to the left. To find that tail to the left, you do 1 minus C, which is our confident level of 95 in this case, and then you divide it by 2, and then you add it to your 95, which is the shaded area. So when you're looking up this value, you're going to end up with 0.95 plus 1/2 times 1 minus 0.95, which will give us an area of 0.975. Then you would put this in the calculator, and then you would end up with your critical value. So when you're putting it in your calculator, you want to make sure you put the degree of freedom in. So you're not putting in the sample size of 15, you're putting in the degree of freedom, and in this case would be 14. So your critical value, again, is 2.145. Pause and try. So whether you looked it up or used the calculator, you should have gotten a critical value of 1.833. Pause and try. So in this case, you should have gotten a critical value of 3.169. So now we're going to be working with constructing confident intervals for a t-distribution. So here's an example. You randomly select 16 coffee shops and you measure the temperature of the coffee sold at each. The sample mean temperature is 162 Fahrenheit with a sample standard deviation of 10. Find the 95% confident interval for the mean temperature and assume that the temperatures are approximately normally distributed. So again, we have a t-distribution. It's meeting that condition. Our sample size is less than 30, and we have our sample standard deviation versus the population standard deviation. And that is key information. So I'm going to identify my mean, my x-bar, my sample standard deviation, the sample size, and my level of confidence C. So in this case, we get 162 is our mean, the standard deviation is 10, the sample size is 16, and we're looking for a confident interval with a confident level of 0.95 or 95%. We are going to be using the calculators to find our interval. So to use the calculator, you're going to hit your stat key, and that's in the TI calculator, and arrow over to test, and in this case you choose number 8, the t interval. Now it's not number 8 in all calculators, so you want to make sure that you're in the right interval, and it should have a t with the word interval next to it. And then you're going to come to this menu. If stat is not highlighted, you want to make sure that it's highlighted. To do that, you arrow over to stat and hit enter, and it will highlight it. And then you'll go down and enter in your mean, your sample standard deviation, the sample size, and the level of confidence. A key note here is that you do not need to enter in degree of freedoms into the calculator because it already does the calculation for the degree of freedom for us. So when you have the data entered in, you're going to press enter and you should get this confidence interval. And in this case, we end up with a confidence interval. Our mean is between 156.7 to 167.3 degrees. Pause and try. So in this case, you should have gotten a confidence interval of 29.5 to 41.5. And what this means is within 95% confident, you can say that the population mean commute time to work is between 29.5 and 41.5 minutes. Pause and try. So in this case, you should have gotten the interval of 71.84 to 88.616. And at a level of 95% confident, you can say that the population mean repair cost is between $71.84 and $88.61. So this next type of confidence interval is for the population proportions. And population proportions, we will be estimating the proportion, the P. And the P is the probability of success in a single trial of a binomial experiment. So when we're talking about the point of estimate for our proportion, our P, the proportion of success in a sample, we will denote it as P hat. And P hat is made up of X over our N, which is our number of successes over our sample size. And again, it's red, P hat. And it's going to be a percentage. So when you're looking for the estimate for Q, the failure percentage, you're going to take your Q, and it's going to be Q hat. You're going to find it by subtracting P hat from 1. And that will give you the percentage of failure for your sample. The round-off rule for interval estimates of proportions is the confidence interval is limited for P hat to 3 significant digits, so 3 decimal places. So let's do an example here. In a survey of 1,000 U.S. adults, 662 say that it is acceptable to check personal emails while at work. Find a point of estimate for the population proportion of U.S. adults who say it's acceptable to check personal emails while at work. So in this case, I'm going to identify my N and my X value. And my N is the sample size, which is 1,000, and my X value, or the success value, is 662. So I want to find my P hat. To find my P hat, I'm going to take my success and divide it by my sample size, and I'm going to find my percentage, or 0.662, or 66.2%. So that would be your P hat. So to find Q hat, you're going to take 1 minus that 0.662, and you'll find your Q hat will be 0.338, or 33.8%. Pause and try. So in this case, your P hat should be 0.11, or 11%, and your Q hat should be 0.89, or 89%. So if we were to manually construct an interval for the population proportion, these are the steps that we would take. And the first step is identify your number of successes and the sample size. Then you're going to find your P hat and your Q hat. You always have to verify that the sample size times the P hat is greater than or equal to 5, and the sample size times your Q hat is greater than or equal to 5. If this condition isn't met, then you would not have a proportion. So it's very important that you double check to make sure that this meets the conditions. And then you can find your margin of error by using this formula. And this formula is going to use that critical value Z based on your confidence level. And it's going to be times the square root of P hat times Q hat, all divided by N. And then you can find your confidence interval by taking P hat and subtracting that error you found, and the P hat and adding the error you found. Now we're going to be doing the construction in our calculators, and the calculator again will do the work for us. So when we have in a survey of 1,000 U.S. teenagers, 372 said that they own smartphones. They're asking us to construct a 95% confident interval for the population proportion of U.S. teenagers who own smartphones. So the first thing I'm going to do is I'm going to identify my X and my N. And in this case, the X is the 372 and my sample size is 1,000. The 95% confident interval, so we're going to go into the calculators. Now be careful when you're looking in the calculator. You're going to go to your stat button, you're going to arrow over to test, and you're going to choose the one that says 1 PROPZ interval. So you want to make sure you're choosing the right option. In our case it says A, but yours could have something different. So make sure it's going to say the same abbreviation, 1 PROPZINT. Choose that option. Once you choose that option, you should see this screen. And in this screen, you want to enter in your X value, and in this case, it's that 372, and you want to enter in your N value, the sample size, which is 1,000, and that level of confidence, which is that 95. And you have to enter it in as a decimal, so it'll be 0.95 that you enter in to the C level. And then you're going to press enter, and you're going to find your confident interval. In this case, our confident interval is 0.342 to 0.402. Pause and try. So you should have gotten a confident interval between 0.626 and 0.702. This next thing that we're going to be working with is determining a minimum sample size. So given a confident level and a margin of error, the minimum sample size N needed to estimate the population proportion is this formula, which is N equals your P hat times Q hat, and then make sure you use parentheses with your critical value Z based on your confident level divided by your error, and you want to make sure you square that value. So a key note here is you will have to find your Q hat, and to find your Q hat, remember it's going to be 1 minus P hat, and you're going to have to also find that critical value C, which will be based on your level of confidence. So the formula assumes you are given a point of estimate for P hat, some percentage. If it's not given, you will use 0.5 for your P hat and 0.5 for your Q hat. So if you're not given a point of estimate, then you're going to use the 50-50 or 0.5 for your P hat and Q hat. If you're given a point of estimate, then you would use that, and you would have to find your Q hat. And a key note is you always have to round up. So please make sure you round up, if you have any decimal, to the nearest whole number. So here we're going to do an example. You are running a political campaign and you wish to estimate with a 95% confident the proportion of registered voters who will vote for your candidate. your estimate must be accurate within 3% of the true population. Find the minimum sample size needed if no preliminary estimate is available. So what that means is there's no preliminary estimate. So that means that your p hat and your q hat, you would use the 0.5. So we're going to find the value for your critical value for your level of confidence here, which is 95%. And our error in this case is that 3%. Make sure you convert that 3% to a decimal, and that decimal would be 0.03. So make sure you're converting it correctly. Your level of confidence here is 95. So your confidence level is 0.95. Make sure when you find that z value for your confidence level, you incorporate the tail into your area. So you're going to find the critical value by incorporating that tail, and you look it into the calculator. You go to your second VARS button, number 3, that inverse norm. That's how you find a z value for an area, and then you get your z value. So in this case, our z value would either be a negative 1.96 or a positive 1.96. And because the formula has a square in it, it doesn't matter if you use the negative or positive, because it'll end up being squared. So now we're going to plug everything in. Again, the p hat, the q hat are 0.5, and then in parentheses you want your critical value, which is that 1.96 based on the level of confidence, divided by your your error, which is that 0.03, and squared. And you could put this all in the calculator just like this, and you should get approximately 1067.11. And you always have to round up. So make sure you round your answer up, and you should have a minimum sample size of at least 1,068 voters. So this next example is you're running the same it's the same example, except for we're given our p hat is 0.31. So instead of it not being given, we're given it. Therefore, we're going to use that, and we're going to find our q hat. So our q hat is 1 minus 0.31, which would be 0.69. We already found our critical value from the previous example, and we found the error, which is 0.03. And I'm going to use that same formula, but now instead of 0.5, I'm using the preliminary estimate that was given of 0.31 and the q hat, which I found. And I will get an answer of 913.02, and you always have to round up. So the minimum sample size in this case would be at least 914 voters. Pause and try. So your first answer should be 601 adults, and your second answer should be 485 adults.